Hello friends, a very good morning to all the students. Am I audible to all the students? Okay, fine. So dear friends, you are aware that we are discussing the important chapter, the third unit of the subject of basic mechanical engineering, one of the important unit, important chapter in context of the theoretical examination. The chapter name, that is the properties of the gases. So friends, if you remember, in the last lecture we have discussed several derivations, we have solved several parameters related to the three non-flow processes. The first process we have covered, that was the constant volume process, which is also known as the isochoric process. The second process which we have discussed, that was the constant pressure process. Another name is the isobaric process. And third one, that was the constant temperature process. And there are different names of the constant temperature process. The constant temperature process is also known as the isothermal process, and since this process follows the Boyle's law, on the PV diagram we are getting the hyperbolic curve. Hence the constant temperature process is also known as the hyperbolic process. And in the constant temperature process, we have done the important derivation, that was the amount of the work done. So the final answer which we have got, that is W is equal to C ln V2 by V1, where C is the constant. In place of C, we can note down C is equal to P1 V1 or C is equal to MRT1. Also, C is equal to P2 V2, that is also equal to MRT2. So I hope you are remembering all those points. Dear friends, let me inform you that today's lecture will be a power pack lecture, because in the today's lecture we are going to discuss several derivations, and I suggest that if you are noting all those derivations in your notebook, then as I am explaining, you will be perfectly understanding the steps of the derivation. So dear friends, before starting our today's session, let me ask you a simple question. We have already discussed the three non-flow processes. So any student can give me the answer, which two processes are remaining to be discussed? Which two processes are left to be discussed? Okay, you can give your answers in the chat box. Okay, some of the students are telling adiabatic and polytropic. Okay, very good. That is one of the perfect answer. So in today's session, we are going to discuss only the two processes, but these two processes are very important in context of the theoretical examination. So in today's session, we are going to discuss several derivations related to the adiabatic process, and finally we will discuss the polytropic process. So the first point, that is the adiabatic process. Dear friends, remember the definition of the adiabatic process. It is one of the important points. So an adiabatic process is a thermodynamic process in which there is no heat interaction during the process. That means during the adiabatic process, there is no heat exchange. Hence, for the adiabatic process, we can conclude that During this process, Q is equal to 0. So this is one of the most important point and the definition related to the adiabatic process. And if we remember the first law of thermodynamics, that is Q is equal to delta U plus W. Since Q is equal to 0, in adiabatic process, the work interaction will be possible only at the expense of the internal energy. The frictionless adiabatic process is known as the isentropic process. Remember friends, the law for adiabatic process, that is PV raised to gamma, that is equal to constant, where gamma is the constant term, that is equal to 1.4, the value always remains constant, and the gamma is also known as the adiabatic index. If we are representing the adiabatic process on the PV diagram, similarly considering point number 1 as the initial state, 2 as the final state, so we are getting this type of the curve, we are getting the area of the diagram, and this area represents the work done. And this curve represents PV raised to gamma is equal to constant. For undergoing the adiabatic process, we are considering an insulated cylinder and the piston to reciprocate in the cylinder. Because of this insulation, we are considering that there is no heat interaction during this process. So friends, out of this, all the points, they are very important and they are frequently asked in your theoretical examination. The next point and the most important point of the adiabatic process, that is the law for the adiabatic process. Dear students, I instruct all the students to off your videos whenever you are joining the meeting. So try to remember this derivation because it is one of the most important question which is asked from this chapter. The law for adiabatic process, that is P capital V raised to gamma, that is equal to constant. Remember friends, here V, that is the capital V, total volume of the gas. Okay, one student is asking, sir, insulated means sealed. Okay, can be considered that it can be sealed or insulated. The technical perspective is because of the insulation, because of the sealing, we are not allowing any type of the heat interaction from the system or to the system. Okay, rule number 62. I hope you have understood this point. Fine. So dear friends, now you can start noting down these steps because it is one of the important questions that can be asked in the theoretical examination. So first point, that is according to the first law of thermodynamics, we can write down this statement: the amount of heat supplied, that is equal to the change in internal energy plus the work done. So now if we are considering the unit mass of the gas, then the first law of thermodynamics can be written in this manner, that is dq is equal to cv dt plus p into dv. Remember friends, here q is small because we are considering specific value. Also p is small and volume is also written in small alphabet. Change in internal energy, we are already knowing, that is CVDT, and work done, that is PD. So now friends, according to the definition of the adiabatic process, we have already understood that there is no heat interaction. So the term dq, that is equal to 0. Substituting this answer in the above equation, finally we are getting that is Cv dt plus P into dV, that is equal to 0. Let us mark this as equation number 1. Dear friends, dear students, I am moving in very steady manner, very slowly I am explaining these steps so that you can note down these steps and also you can remember how we are proceeding further in the derivation. So this is equation number 1. Now dear friends, we already have understood and studied that according to the characteristic gas equation, that is PV is equal to RT, because in the characteristic gas equation we are considering mass, that is equal to 1 kg. Now friends, on differentiating this equation, we will be getting the answer. So on differentiating this equation, now we will be getting the answer. So some of the students are telling how we are getting equation number 1. Dear student, it is very easy to understand. The heat supplied, that is equal to change in internal energy plus the work done. We are considering the unit mass of the gas. So for unit mass, we need to consider the specific values of the different quantities. So I am writing down dq is equal to Cv dt plus P into dV. Now for adiabatic process, we have already understood in the definition that is dq is equal to 0. So thus I can write down Cv dt plus P into dV is equal to 0. That is equation number 1. Now we have the characteristic gas equation, that is PV is equal to RT. On differentiating this equation, we are using the simple differentiation, that is d by dx of u into v. So that is equal to u dv by dx plus v du by dx. I hope you remember, but in this case we are not having any x. So we will be eliminating that term of the x, and finally we are getting this answer on differentiating the characteristic gas equation, that is P into dV plus V into dP is equal to R into dt. I hope you have understood up till this point. So from this equation, now I will be getting the value of dt. So dt is equal to P into dV plus V into dP divided by R. Substituting this value of dt in equation number 1. Substituting this value of dt in equation number 1, we will be getting this answer, that is Cv into Pdv plus Vdp divided by R plus P into dV is equal to 0. Now friends, multiplying R on both the sides and substituting the value of R, that is Cp minus Cv, elaborating all the brackets, removing all the brackets, doing the multiplication, you will be getting 4 terms. Out of these 4 terms, 2 terms will be the same terms, but one term will be having positive sign, the another same term will be having the negative sign. So both these terms will be cancelled out, and only 2 terms will be remaining, and those 2 terms will be like this, that is Cp P into dV plus Cv V into dP, that is equal to 0. That is equation number 2. So I hope you are getting this answer of equation number 2. I want your responses in the chat box. If you are doing the derivation with me, are you getting the answer? That is equation number 2. as I have written? Okay, fine. Thank you all. Majority of the students are getting the answer. That is equation number 2. So now friends, let us proceed further. Taking the same equation number 2. Now we are going to divide the equation number 2 by CV V into P. Remember friends, we are taking the volume that is small v, that is specific volume. So dividing the equation number 2 by this quantity, that is CV V into P. So on dividing, I will be getting the equation in this manner. So we can cancel the similar terms from the denominator and the numerator, and finally we are getting this type of the answer, that is Cp by Cv into dV by V plus dP by P is equal to 0. Now friends, if you remember, Cp by Cv, that is equal to gamma, that is always a constant value, that is equal to 1.4, and gamma is known as the adiabatic index. So substituting that value of gamma, I am getting this equation, that is gamma dV by V plus dP by P is equal to 0. I hope you are getting this answer of equation number 3. I want your responses in the chat box. If you are understanding the steps of the derivation, gamma dV by V plus dP by P is equal to 0. Okay, good. Majority of the students are understanding and also they are noting down these steps. Very good, students. So now on integrating equation number 3. Now we are going to integrate the equation number 3. But friends, remember, during the integration, we are not take the limits of the integration. We will do the simple integration. So on integrating equation number 3, I will be getting gamma integration dV by V plus integration dP by P is equal to integration of 0. So on integrating that parameter, integrating equation number 3, I will be getting this answer, that is gamma into ln V plus ln P is equal to ln C. Because dear friends, remember integration of 0, that is a constant term, and in order to remove the ln from both the sides, I am writing that answer, that is ln C. So now friends, I can take the value of gamma to the head of V. So I will be getting the answer, that is ln V raised to gamma plus ln P is equal to ln C. So there are ln throughout this equation, so I can remove the ln, and finally I will be getting this type of the equation, that is P into V raised to gamma, that is equal to constant. And this equation is known as the Poisson's law. So the above equation 4 is known as the Poisson's law. Remember friends, in the Poisson's law, the volume is considered as the specific volume till we have not reached our final answer, that is law for the adiabatic process. So first we have got the answer of the Poisson's law. In the Poisson's law, the volume, that is specific volume, that is denoted as small v. I hope you are getting the equations, you have got the answer. I want your responses in the chat box if you have understood up till this point. The concept is clear, the derivation is clear. Up till the Poisson's law. Okay, fine. Getting the good responses, also the thumbs from majority of the students. So let us proceed further in the derivation. We are already having this equation, that is equation number 4. Now we know that specific volume, that is small v, is equal to capital V by M. So substituting the value of small v, that is capital V by M. So I can write down P into V by M raised to gamma is equal to constant. So I will be getting the answer P into V raised to gamma divided by M raised to gamma, that is equal to constant. M raised to gamma multiplied by the constant, that is again the constant. So final answer I will be getting thus P into V raised to gamma, that is equal to constant. And this equation number 5, that is known as the adiabatic law. So if you see perfectly, this is the equation number 5 and this is the law for the adiabatic process. Now we have reached to our final answer for which we have made this derivation. And dear friends, it is one of the important questions which is asked in your examination. I hope you have perfectly written all these steps and also you have understood these steps. You have understood the method, how we have reached to the law for the adiabatic process. Okay, fine. Thank you all. So now let us proceed further. The amount of the work done. So we are knowing that work done, that is equal to P into dV. So the total work done, that is W is equal to integration of P dV between the limits V1 and V2. So for adiabatic process, we now already know that is P V raised to gamma is equal to constant. So I can write down P is equal to C upon V raised to gamma. So substituting this value of P in this equation, we are getting the answer, that is W is equal to integration of C upon V raised to gamma dV between the limits V1 and V2. So here C is the constant term, so it is removed from the integration. So I am getting the answer, that is W is equal to C integration of V raised to minus gamma dV. So I hope friends, if you remember integration of x raised to n dx, that is equal to x raised to n plus 1 divided by n plus 1. But in our case, the value of small n, that is equal to minus gamma. So on integrating, I will be getting the answer, that is W is equal to C V raised to minus gamma plus 1 divided by minus gamma plus 1 between the limits V1 and V2. And I have got this type of the answer by using the concept of this integration. Using the integration x raised to n dx. But in my case, the value of n, that is minus gamma, x is capital V and dx is dv. I hope dear students you are understanding the points. Now if I am substituting the limits in the equation, then I am getting this type of the answer, that is W is equal to C V2 raised to minus gamma plus 1 minus V1 raised to minus gamma plus 1 divided by minus gamma plus 1. That is my equation number 1. So friends, we have already derived, that is C is equal to PV raised to gamma, that is equal to constant. So I can write down C is equal to P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So I will be multiplying this C in the bracket. So CV2 minus that CV1. When C is multiplied by V2, we are going to substitute P2 V2 raised to gamma. And when C is multiplied by V1, we will substitute P1 V1 raised to gamma. Then elaborating the brackets, we will be getting V2 raised to gamma into V2 raised to minus gamma. Both these terms will be cancelled. Similarly, on the next side, V1 raised to gamma into V1 raised to minus gamma, that again will be cancelled. So finally, we will be getting this type of the answer. So substituting the value of C in equation 1 and then rearranging the terms, finally we are getting this type of the answer, that is W is equal to P1 V1 minus P2 V2 upon gamma minus 1. Okay, so W is equal to PdV. So W is equal to integration of PdV between the limits V1 and V2. For adiabatic process, P V raised to gamma is equal to constant. So P is equal to C upon V raised to gamma. So in place of P, I am substituting C upon V raised to gamma into dV between the limits V1 and V2. C is the constant, so it is removed from the integration. So C integration of dV divided by V raised to gamma between the limits V1 and V2. Now for this integration, I am taking the logic of this integration. Integration of x raised to n dx. So that answer is x raised to n plus 1 divided by n plus 1. But in my case, you are seeing that I will be getting integration of v raised to minus gamma into dv. So my n will be minus gamma. So I am writing the answer C v raised to minus gamma plus 1 divided by minus gamma plus 1 between the limits V1 and V2. Now I am opening the limit, so I am getting this answer, that is W is equal to C V2 raised to minus gamma plus 1 minus V1 raised to minus gamma plus 1 divided by minus gamma plus 1. That is my equation number 1. Now we know that C is equal to P1 V1 raised to gamma, that is also equal to P2 V2 raised to gamma. So C, when it is multiplied by the V2 term, we are substituting P2 V2 raised to gamma. When C is multiplied by V1 term, we are getting P1 V1 raised to gamma. So then elaborating all the brackets, in the first one we will be getting V2 raised to gamma multiplied by V2 raised to minus gamma. So both these terms will be cancelled. So we'll be getting the answer P2 V2 minus the second term we will be getting P1 V1 divided by minus gamma plus 1. So taking the negative signs common. Finally, I am getting this answer, that is W is equal to P1 V1 minus P2 V2 upon gamma minus. So in place of P1 V1, I can write down that is W is equal to MRT1, and in place of P2 V2, I can also write down that is MRT2 divided by gamma minus 1. So I hope now the concepts are clear to the majority of the students. So let us proceed further. Relation between pressure, volume and temperature. So we know that PV raised to gamma is equal to constant, adiabatic law. PV by T is equal to constant, that is combined gas law. So dividing both these equations. So this is the division of the equations. P is the common term, so it is cancelled out. Hence we get T into V raised to gamma minus 1, that is equal to constant. Thus, finally, we get the relation considering the initial and the final states. So that is T1 by T2 is equal to V2 by V1 raised to gamma minus 1. That is my equation number 1. Moving further, we already know that P1 V1 raised to gamma is equal to P2 V2 raised to gamma, that is adiabatic law. So taking volume on one side, pressure on another side, I am getting the answer V2 by V1 raised to gamma is equal to P1 by P2. So V2 by V1 is equal to P1 by P2 raised to 1 by gamma. I hope this is the simple mathematics which you have already studied. So substituting this value of V2 by V1 in equation number 1, Substituting this value of V2 by V1 in equation number 1. Here I will be substituting that answer. So finally we are getting the relation, that is T1 by T2 is equal to P1 by P2 raised to gamma minus 1 divided by gamma. So this is the relationship between the pressure, volume and temperature. Remember friends, all these equations we are going to use for solving the numericals. Next, now the change in internal energy we have already understood and remembered that there is only one equation, that is delta U is equal to mCV T2 minus T1. Also, according to the first law of thermodynamics, we know that Q is equal to delta U plus W. But for adiabatic process, Q is equal to 0. So delta U is equal to minus W. Amount of heat transfer, according to the definition, Q is equal to 0. Change in enthalpy, standard equation, that is delta H is equal to mCp T2 minus T1. So dear students, I hope you are understanding these points. So with this we are completing the adiabatic process. Remember, in the adiabatic process, it is a thermodynamic process in which there is no heat interaction. That means for the adiabatic process, Q is equal to 0. Now friends, let us proceed further to the last process, that is the polytropic process. The polytropic process is the most commonly used process in the practice for determining the properties of the gases. The standard equation for the polytropic process is given as PV raised to N, that is equal to constant, where N is the polytropic index and the value of N, it varies from minus infinity to plus infinity. But for the practical purposes, for determining the properties of the gases, we are generally taking the index N to be in the range of 1 to 1.7. This is the simple PV diagram representing the polytropic process. Here equation we have mentioned, that is PV raised to N is equal to constant. So this is an important figure. So dear friends, from the polytropic process we can easily derive all the 4 processes which we have studied. The standard equation for polytropic process, that is PV raised to N is equal to constant. If I am substituting N is equal to 0, then I will be getting the answer, that is P is equal to constant. So that is constant pressure process. If I am substituting N is equal to infinity, the term raised to infinity, that term will be a constant term. So I will be getting PV raised to infinity, that is equal to constant. So the term volume is the constant term. So when N is equal to infinity, it is the constant volume process. Again now when N is equal to 1, so PV is equal to constant. So PV is equal to constant, that is Boyle's law, and Boyle's law can be applied for the isothermal process. So when N is equal to 1, it represents the isothermal or the hyperbolic process. And dear friends, if we substitute N is equal to gamma, N is equal to 1.4, then we are getting the answer, that is the adiabatic process. So from the common equation of the polytropic process, we can easily derive the different 4 processes. Let us proceed further in the derivations of the polytropic process. Polytropic process is much similar to the adiabatic process. Only we will be replacing gamma by small n, where small n represents the polytropic index. And the value of small n will be a variable value. So doing the same procedure as we have done in the adiabatic process, only substituting N in place of gamma, we are getting the answer of work done, that is W is equal to P1V1 minus P2V2 upon N minus 1. Also we can write down that is W is equal to mRT1 minus mRT2 upon N minus 1. Relationship between pressure, volume, temperature, standard equation, PV raised to N is equal to constant. So P1V1 raised to N is equal to P2V2 raised to N. Similarly, the equations can be written for temperature and pressure and temperature and volume. Change in internal energy, our standard relation, that is delta U is equal to mCV T2 minus T1. And change in enthalpy, again our standard relation, that is delta H is equal to mCT T2 minus T1. Dear friends, now remember for the adiabatic process, the amount of heat transfer was equal to 0. But for polytropic process, is it not 0? So we need to derive the equation for the amount of heat transfer. So this is the derivation. According to first law of thermodynamics, Q is equal to delta U plus W. Substituting the value of W and delta U. Now in place of CV, I am substituting R upon gamma minus 1. Then elaborating the brackets, cancelling the common terms, taking the common terms on one side, you will be getting this answer, that is Q is equal to gamma minus N upon gamma minus 1 into P1V1 minus P2V2 upon N minus 1. Now friends, we have already known that this term P1V1 minus P2V2 upon N minus 1, that is nothing but equal to W. So I can write down Q is equal to gamma minus N upon gamma minus 1 into W. Okay, I hope the steps are clear to you. About the amount of the heat transfer, I want your responses in the chat box. If you are understanding the points. Okay, good. Majority of the students have perfectly understood, and also they are making the derivations in your notebook and they are getting the answers which I have also mentioned in my presentation. So friends, with this I am concluding the session from my side. Thank you for watching the session. Have a nice day. See you in the next lecture. Dear friends, remember with this I am completing the theoretical points, the analytical points of the chapter of the properties of the gases. From the next lecture of the BME, we are going to solve the numericals of the chapter of the properties of the gases. So be ready with the notebook, pen and the scientific calculator. So we are going to solve several numericals, different numericals in the chapter of the properties of the gases. So now if you are having any question, you can ask me. Sir, can you show the before slide? That means which slide you are asking? Roll number 71. I am not getting your question. What do you mean by before slide? All the students, please specify your question so that I am able to understand. For work done of the polytropic process, see, for the work done of the polytropic process, the same method we will be following as we have done in the adiabatic process. In the adiabatic process, we have taken V raised to gamma, but in polytropic process, we are going to take V raised to small n. Only the gamma will be replaced by small n. Rest all these steps will remain the same. And for the adiabatic process, for the polytropic process, we'll be getting the same answer as that of the adiabatic process. Only the change will be in polytropic process, gamma will be replaced by the polytropic index. I hope roll number 71, I have answered your question. Roll number 71. Now we have understood the point. Okay, some examples of the adiabatic process and the polytropic process. As we are discussing some other chapters, you will be getting these examples of the adiabatic process and the polytropic process. Okay, but practically if we want to understand, these processes are used for determining the properties of the gases. Okay, roll number 85. Have you got the answer of your question? Any other questions from the students? Okay, no need to refer to this slide, dear friends. You can refer in your textbook. I have mentioned all these points in the same manner as they are given in the standard textbook. Okay, so no need to worry, but while you are referring your textbook, if you are not understanding any of the points, then you can ask me at that point. Okay, roll number 62. Understood the point? Just try to remember the main steps which I am highlighting, so that whenever you are referring in your textbook, you can directly catch up those important points and you can understand the steps of the derivation. So I hope now there are no further doubts of any of the students. So with this, I am concluding the session from my side. Thank you all. See you in the next lecture with the discussion of the numericals of the chapter of properties of the gases.